Welcome. These are lectures on the second unit of the year, atomic structure, and this would be our second lesson, experimental evidence for atomic structure. This follows from the text we read in the beginning. First of all, J.J. Thomson's plum pudding model. First, the background was he had discovered an electron using this cathode ray tube, which led him to conclude that the atom was a positively charged matrix, or a jelly, in which negatively charged particles were suspended. If we had to model this, as he said, the atom was a positively charged pudding. This is a famous traditional British dessert, plum pudding. The pudding was positive, uniformly positive throughout, and in this pudding were these negatively charged plums, these particles that were suspended somehow within this overall positive jelly. How did he determine that you had things called electrons? Well, he used a cathode ray tube. He supplied electricity to this cathode ray tube, also called a Crookes tube. He had created a near vacuum inside. He removed all the air, so there were only a few particles of air in here. And when he supplied energy to the cathode ray tube, it generated an emanation, a brilliant light. And when he placed a negative and a positive plate, he noticed that this emanation of light tended downward toward the positive side. So he reasoned that this emanation must be negatively charged. And he also reasoned that it only could flow because of this near vacuum. There wasn't much resistance to the flow of what? Well, he reasoned that this must be particulate in nature. It must be made of particles. And so therefore electrons were negatively charged particles. Negatively charged again because that stream of electrons would be attracted towards a positive plate. Now, as we said in the previous lesson, Ernest Rutherford's goal was to determine whether this model was correct or not, or was in need of revision. So he shot these positively charged alpha particles at a thin foil of gold, only a few atoms thick. Before going to the experiment, he thought that if his teacher, Thomson, was correct, if the plum pudding model was essentially right, the following would happen. His alpha particles, which were positive in charge, should all fly through with little to no deflection, just like this. So if you were to observe them on the other side, you would observe that they would all fly through. Now, what actually happened? Well, here's our thin foil of gold right there. Here's our source of alpha particles, and here's what he saw. He saw that mostly as he expected, they flew through. And I'm getting ahead of myself. The construction. What is this outer perimeter? This is a zinc sulfide screen. It is what we call phosphorescent, meaning that when an alpha particle strikes it, it glows. And if you are observing from outside, so you have a little microscope, here's my idea of an eye, you can actually see flashes happening. So of course you would see that mostly you have flashes here right opposite the source of the alpha particles. But also, when you observe from other spaces, you notice that you also have flashes here, which must mean the following, that although most of them passed through without deflection, a few of them were deflected to some degree. Some even bounced back directly at the source. A few did this. What's going on here? Why are most passing through without deflection, but why are a few being deflected? This is the conclusion that Rutherford drew. He said because most of the particles are flying through like so, without any deflection, that the atom must be mostly empty space. Because a few of them were being deflected, well, to be deflected, you have to be deflected off of something. That something was a positively charged nucleus in which all or the overwhelming majority of matter was concentrated. So it stands to reason if most of your atom is empty space, that means your mass had to be in one particular area, which he called, or came to be called, the nucleus. Since you have these alpha particles, once they encountered the positive nucleus, they bounced off. They bounced off in different directions. So again, the atom is mostly empty space because most of the alphas pass through. Mostly empty. But you have a nucleus that was dense, in which, as I said, most of the matter of the atom was concentrated. Of course, dense implying small, smaller than the atom, and of course, positive in its charge. So that's a look at the experimental evidence in detail. I hope you enjoyed it. That was our second lesson.